Chapter 2 is roughly divided into a crash course on chemistry and an intro to cell biology. Chapter 3 covers some of the practical applications of biochemistry in nutrition, as well as membrane transport into and out of the cell. In many traditional biology textbooks, the chemistry sections of these chapters would actually take up about 2 to 3 full chapters on their own. So realize as you're reading these chapters that we're really only touching on the surface a lot of these topics. That actually can make it a little harder to understand rather than easier, because there are so many vocabulary terms that are just packed into that material, and it can get a little overwhelming. So because of this, I'm actually going to give you more than just a short intro to these chapters. My plan here is to do about a 3-part narrated PowerPoint. The first 2 parts are going to have to do with chemistry and biochemistry, and the third part is going to go over the parts of the cell and cell membrane. In addition to these multi-part narrated PowerPoint presentations, I'm also going to have a whole lot of videos under the additional resources section of this week's Blackboard folder. So you won't be tested over the extra videos, but if you have time, I strongly suggest watching them either before or after reading that section in the textbook. I really think it'll help you understand those vocabulary terms and kind of the tricky parts that are in the textbook. Okay, so let's start off with a reminder about elements. Elements are the fundamental forms of matter that have been identified in the world around us, or some of them have actually been created by scientists in labs. All of the known elements are found on the periodic table, which is what you see here in front of you, where they're grouped according to similar characteristics and similar chemical behavior. All of the elements have 1 to 2 letter abbreviations, and those are the abbreviations that are used in the chemical formulas or in chemical equations that you'll see. Examples of elements include hydrogen, which is indicated by an H, that's on the upper left-hand side of the periodic table. Carbon, which is indicated by a C, kind of in the right-hand side, second row. And oxygen, indicated by an O, which is kind of near carbon on the right-hand side of the screen there. The atom is the smallest unit in nature that has the properties of any given element. So atoms cannot be broken down any further by normal chemical means like boiling. Atoms are made up of 3 subatomic particles: protons, neutrons, and electrons. Protons and neutrons are larger particles, and they're found clumped together in the nucleus, or the center of the atom. Electrons are very, very small and are found in energy rings that are spinning around the nucleus. Protons are positively charged. Electrons are negatively charged. Neutrons don't really have a charge. They're really considered to be neutral. In a balanced atom, there will always be the same number of protons, neutrons, and electrons. So if there are 3 protons, there would be 3 electrons. There would also be 3 neutrons in a balanced atom. Going back to the periodic table for just a moment, you'll notice that each element has several numbers in its box, in addition to its name and its abbreviation. So here's a close-up view of carbon. The symbol for carbon is an uppercase C. The atomic number is 6. That is the total number of protons in each atom of carbon. The atomic weight is 12.01. Remember how I said that in a balanced atom, the number of protons, neutrons, and electrons is the same? Well, the atomic weight is a combination of all of those subatomic particles. So each proton and each neutron has an atomic mass unit of 1. In a balanced carbon atom, you've got 6 protons and 6 neutrons, so that equals 12. The 0.01 in the atomic weight comes from the teeny, teeny, tiny electrons. So very, very small that 6 of them only equals 0.01 atomic mass units. However, even though electrons are very small, they are still extremely important. Electrons spin around the nucleus of the atom in a variety of energy levels that are also sometimes called shells. The shell closest to the nucleus, indicated here by the arrow, can only hold up to 2 electrons, but every other shell after that can hold up to 8 electrons. So carbon atom here has just 2 shells, because that's the whole total number of electrons it has. Is 2 for the inner shell and 4 for the outer shell. But if you have an atom that has more electrons, you can continue to add shells after the first and the second one. But after that first one, the rest can only hold up to 8. The outermost shell is called the valence shell. So for the valence shell to be complete, it needs to have 8 electrons. And every atom wants to be complete. So they will beg, borrow, and steal electrons to complete their valence shell. If an atom has 4 or 5 electrons in its valence shell, like carbon here, it tends to play nice and share electrons with other elements. If an atom just has 1 or 2 electrons in its outer valence shell, it wants to get rid of the electrons it has, so it tends to donate those electrons to other elements. If an atom loses electrons, that means it's losing a negative charge. So it gains a positive charge because the number of protons will then outnumber the number of electrons. If an atom has 6 or 7 electrons in its outer shell, it tends to take electrons from other elements. So let's look at a fluorine atom. Fluorine has an atomic number of 9. That means in a balanced atom, there will be 9 protons, 9 neutrons, and 9 electrons. So if 2 electrons occupy the innermost shell, that leaves 7 electrons in the outer valence shell. So fluorine only needs 1 more electron to be complete. So it has a nasty tendency to kind of steal electrons from other elements, and that gives fluorine a total of 10 electrons, but only 9 protons. So fluorine would then have a negative charge due to that extra electron. The term for any charged atom is an ion. Once fluorine becomes charged, its name actually changes. It changes it to fluoride, which I'm sure you've heard of. The addition of fluoride to drinking water is one of the best dental breakthroughs of modern science. So all this talk of electrons brings us to the concept of chemical bonds. Chemical bonds form when atoms share or exchange electrons. When atoms donate or accept electrons, they form an ionic bond, which is a bond between 2 ions. When atoms share electrons in an attempt to complete their valence shell, they form a covalent bond. If the electrons are shared equally between the 2 atoms, that bond is called a non-polar covalent bond. That's kind of indicated at the top of the screen here. If the electrons are shared unequally, so that is one atom has the electrons more of the time than the other atom, that bond is called a polar covalent bond. So in polar covalent bonds, each atom will actually have a partial charge, either partially positive or partially negative, just because of how the tendency of the electrons to kind of hang out more around one atom versus the other. So now let's look at a water molecule. Water's chemical formula is H2O, so that's 2 hydrogen atoms that are bonded to 1 oxygen atom. Here are 3 different representations of a water molecule. The one on the top left shows the electron shells and the sharing of electrons in those shells. Because the oxygen atom is more electronegative, that means it has a stronger attraction to electrons, than the hydrogen atoms, the electrons spend more time around the oxygen. So that gives the oxygen a slightly negative charge as compared to the hydrogen atoms, which will have a slightly positive charge. So therefore, because of that distribution of the charge, a water molecule is considered polar. It has a negative region and a positive region. The water molecule at the bottom is drawn according to how an organic chemist would show the molecule. So the straight lines between the atomic symbols represent the chemical bonds between those elements. You'll see this method of drawing organic molecules kind of later in the chapter when we discuss the macromolecules of life. So just think whenever you see the symbols connected by lines, that means that there's a chemical bond between those 2 atoms. The polar nature of water is what gives it some really, really cool features. The negative end of a water molecule is attracted to the positive end of another water molecule, and that's actually called a hydrogen bond. It has its own name. Hydrogen bonds give water cohesiveness, where the water molecules tend to stick together. Plants depend on cohesion to transport water from roots, from the bottom of the plant, up to the top of the plant. Also, when heat energy is added to water, the hydrogen bonds absorb a lot of that energy. So the hydrogen bonds actually have to break from all of the different water molecules before the overall temperature of the water will increase from the added heat. So this is why it takes so very long for water to boil as compared to other liquids like alcohol, which boil and evaporate without having to add too much heat. Water's polarity is also the reason it's often called the universal solvent. Any polar or ionic compounds that are added to water will dissociate or separate because the negatively charged ions or the ends of the polar compound will be attracted to water's positive hydrogen end, and the positively charged ions or ends of the polar compound will be attracted to water's negative oxygen end. So that's why you can dissolve sugar or salt in water, is because those compounds will dissociate or separate because of the polar nature of the water molecule kind of pulls them apart. But that's also the reason why you cannot really dissolve oil in water. Oil is nonpolar, so it doesn't have any negative or positively charged ends, and so it's actually repelled by water. Substances that are attracted to water are called hydrophilic compounds, and substances that are repelled by water are called hydrophobic compounds. These two terms will be important later on in the section on organic chemistry and the cell membrane. However, before we move on to that, let's take a moment here, a second, to look at acids and bases. So acids are substances that donate hydrogen or H+ ions into a water solution. What that means is if you put something like hydrochloric acid into water, it's going to dissociate or separate into a chloride ion and a hydrogen ion. The stronger the acid, the higher the percentage of molecules that will dissociate when they're added to water. So the higher the concentration of the hydrogen ion or the H+ ion in solution. Bases are substances that will donate hydroxide or OH negative ions into a water solution, or they can accept hydrogen ions in solution. So the stronger the base, the more likely it is to dissociate in the water. And that means that the stronger the base, the higher the concentration of hydroxide ions in solution. So what we've got here is a pH scale that will measure a substance's relative acidity or basicity. That's also called alkalinity sometimes. But the lower the number, the more acidic the substance. So if it's more acidic, it's going to have a greater concentration of hydrogen ions. The higher the number, the more basic or alkaline the substance is. So if it's a higher number, there's a greater concentration of hydroxide ions. A pH of 7 is considered neutral. So a pH of 7 is the pH of pure. Alright, so that's the end of part 1. Part 2 is going to discuss organic chemistry and biochemistry, and that will be the next video.